Good morning, or good afternoon, no, good morning. Welcome, Russia. I'm Rolf Huisman. Thank you for having me. And I'm going to talk today and introduce you into the world of quantum computing. Ooh, I'm getting some feedback here. And the thing that people always want to know is like, quantum computing, I hear about it all the time in papers and things like news articles, but why do I even need this? I mean, is it just a fad, or what's the uses of this? And once I start talking about it, it's like, okay, yes, this is something I'd like to do. It's like, okay, how can I do this? How can I play with this? How can I enable this? Yeah, wait a minute first. You first need to understand some basic concepts, so we're first going to talk about those. So let's first start with the first one. What is the impact of the quantum computer on your life? And to imagine what kind of impact a quantum computer would have, I'm going to start with the biggest impact on my life. This is Waffy. It's my daughter's stuffed animal. And as might of you people know who have children, are there people which have children here in the room? Yeah, a number of them. As you might know, people and kids mostly lose this thing. So Waffy might be in a washing machine, somewhere located somewhere else, or it's just in the toy cabinet located there. And every time she needs to go to sleep, yeah, Papa, I can't sleep without Waffy. I really need Waffy. So it becomes like tracking the Waffy through our house. Now, some people might add like, yeah, you could place a tracker on the darn thing. But this is something that my wife didn't approve of, so I needed to have a different solution on this. So this is like the logical layout of my house. And we first start in the bedroom of my daughter, where we start the hunt for Waffy. So we first move downstairs to the living room, where the toy cabinet is. We see if it's there. We move to the top attic, where the washing machine is, like, is he there? And then we arrive to her bedroom, where she finally can get to sleep. Because we don't know where Waffy is, we need to go through all the paths in all the places within my house. So what I was thinking about, okay, she needs to be up in her bed at a quick time. I'm going to optimize the path through my house to search for this stuffed animal. And this might sound something familiar, because other companies, which are things like shipping companies, etc., they do the same, with many dimensions, with many starts, a lot bigger. And people who are a little bit familiar in this field might have already recognized this. This is the traveling salesman problem. You want to get through all the nodes, the shortest path through all the nodes in the system. And the thing is, this problem is NP hard. It's a problem which scales exponentially. Okay, if I have many dimensions and it's slow, etc., we have Azure, we have the cloud, we have dynamic scaling. We can scale indefinitely. We have data centers. We can hire and just put money into the problem. Yes? Okay. So, yes, but exponential scaling will not help here. I mean, if you have the story about the grain of rice and you double it for a chessboard, you wouldn't reach the bottom of the board without expanding every rice of the global production. If you just have 1,000 machines, you're not going to make the bottom of the board here. So we need, like, for example, within artificial intelligence, weather predictions, DNA computing, chemistry, etc., we have a lot of these kind of algorithms. So we need a better plan. So our new plan is quantum computing. The quantum computer which uses qubits. Well, the classical computers most people are familiar with have a bit. That's the elementary unit. It's either 0 or it's 1. If you look at a quantum computer, you have both 0, 1, and it can be both at the same time. This is what we call a superposition. If you take a number of these qubits, like an n number, what you're going to see is that you can combine these qubits together. We call this entanglement. That entanglement, that bunch of qubits together, where a normal 2 bits can just have one value, one state. 2 qubits is already 2 to the power n of states at the same time. So if you add qubits there, its range possibilities, its state will grow exponentially. And it can work with that state directly at once. So many people think like, okay, so quantum computers are exponentially more powerful than normal computers. Yeah, close. It's not that simple. There are some restrictions in there. But you can imagine that a 20 qubit machine is something we can still emulate on a normal computer. A 40 qubit machine, that's something that requires a complete data center to simulate. The 72 qubit machines of certain companies, that's not simulatable. That's more powerful than a complete data center. Imagine that, one computer as powerful as a complete data center. So as you can imagine, a lot of companies in the cloud computing space are investing a lot of money in, multi-billion investments on cloud computing and getting these things to work. Okay, so this is something we want to have because it's going to make things possible. So what does this look like? What does this machine look like, this magical machine? Well, a quantum computer usually looks something like this. This is the quantum computer of IBM from IBM Q. And what you see is a delicate frame with all kinds of tubes on them. And the tubes and such are made by a Swedish company. And this complete thing is dumpled in liquid helium to cool. So what goes on is on the top there are a lot of microwave emitters. Let's put it like radio stations. You have a 5 gigahertz Wi-Fi signal, a bunch of Wi-Fi routers are on the top, and they put in 5 gigahertz channel noise like signal into the downward stream. So all those small tubes you see are wave ducts to put those radio signals into the chip. Why are they curled like this all? This is dumped in liquid helium. If they would be straight, they would break from stress. Then in the bottom of the chip, the really, really bottom part, the silver thingy on the bottom, is a chip. And this chip is where the magic takes place. It's a physical machine where quantum operations take place, shielded from most of the noise by cooling it to near zero. We're talking about 12 microkelvin here, in order to phase out all the noise and to make these quantum mechanics principles go to work for us to do our computation. So people are like, that's nice, that looks great. That's something I put in my basement, and then, how do I put a screen to this? Where's my keyboard? Can I play Crysis on this? Well, stop there. That's not how you should think about quantum computers in this case. You should think about quantum computers more as an acceleration card, like in coprocessor in this case. How it works is you have a traditional computer next to the quantum machine. And what you do is you have your problem, in my case my stuffed animal problem, and I formulate it as a quantum circuit. This is the quantum bits, the qubits, and how they're representable. We'll talk about it later. And I have my gates on them to do some computation to make a puzzle. I then give that puzzle to the quantum computer. Well, like I said, that thing is a big radio transmitter boiling down into a small chip performing calculations there. So what happens there is the processing takes place, the quantum principles take place, and I start measuring. And I'm not doing it once, I'm doing it multiple times. When I get these from samplings, these measurements, I eventually get a statistical curve, like a statistical outcome, like I have seen these kinds of outputs this many times. And I interpret this as the result of my computation. So let's go a bit deeper. So, in the keynote, you guys all saw the waves of the QuArC radio and all the phase manipulations. The mathematical model we normally use for that is a two-dimensional vector in complex space. Well, that's a bit mouthful. So what we usually do is we represent it as a sphere, because it's a unity vector. We call this sphere the Bloch sphere. So what we have is 0 at the top and 1 at the bottom. And then we have a vector in that space which has a certain angle called theta. Depending on that angle, if it's more to the top, it's more likely to be a 0. If it's more to the bottom, it's more likely to be a 1. If it's anywhere except the poles, that means it's both at the same time, a superposition. So suppose I take this Bloch qubit and I would have this composition. So what would happen once I observe this? Because this is something I can't see. I pick up the Bloch sphere, this qubit, and observe it. And every time I observe something within a qubit, the superposition disintegrates. And it becomes either the traditional bit, a 1 or a 0. So I first take my first qubit. I do stuff to it and I observe it. It's a 0. Okay, nice. Throw it away. Take another one. Do the manipulations again. I look at it, it's again a 0. Throw it away. Then it's a 1. Okay. 1, 0, yeah. Seems like random. If I turf them down, write them down, what I will see is I get the same distribution as that I expected from the angle I defined in there. So in this case, I would have a 75% 0 chance and a 25% 1. But it won't be exact, because I'm looking at individual qubits. If I perform that multiple times, more often, I will get closer and closer to this kind of distribution. Okay, so I now have this qubit which is essentially that kind of a randomizer. Now I'm going to perform operations on them. So the first gate we use is the X gate, Pauli exclusion. What it basically does is it takes the qubit and it rotates it around. If it's a 0, it's now a 1. If it's a 1, it's now a 0. If it's both at the same time, it's still both at the same time. Okay, so that's nice. So we have a different gate, and this gate is very fundamental to quantum computing. It's the Hadamard gate. And what it does, it brings one which is on the top, a 0, and it brings it into a superposition. It brings it to the x-axis. That makes it a 50-50 distribution of being true and false. Now, I can continue on and on and on, but there are a lot of these rotations of that single qubit. Just take them for granted for now. So this is just one qubit. I want to have multiple qubits combined with each other. This is where the CNOT gate comes in. So if I have a 0 qubit, one which evaluates to 0, nothing will happen to the second qubit I add to the bottom. If I put a 1 in there, I get the reverse at the bottom. So I'll let you have a think. What do you think happens if I put in a superposition in the top? Any ideas? Just make the mental model. So it's a superposition on top. It can be 0 and 1, and it's a 0 on the bottom. If it's a 1, it will become a 1. Yeah, but it's also a 0, but then nothing happens. So what you will see is you have 2 qubits coming out, and these 2 will be correlated to each other. If one is 0, it's 0, the other one is 0 as well. If one is 1, the other one is 1 as well. This is called entanglement. It's still random. You observe it, you get a random answer, either a 0 or a 1. But these two things will be correlated to each other. If you start adding these things together, this is how a quantum computer is built upon. These are the basic building blocks. So how do we program for this kind of thing? Because, okay, this is quantum theory, how this works. Well, to help programmers program for this, Microsoft Quantum, formerly Station Q, made a language. This used to be called an F# extension called Liquid, But they promoted it to a real language within the Visual Studio development kit. It's called QuArC. And if you install the SDK, you get a QuArC application within your start menu, and you can just create a new application. So let's see what this looks like. So as I already mentioned, you have a traditional part and you have a quantum computing part. Welcome to QuArC, the most basic program. It ends on QS and you define a quantum operation. This quantum operation is the layer between the traditional computer and the quantum operations, quantum circuit you define underneath that. So as we already discussed, we have the Hadamard gates and all the other gates to create a superposition. So let's do that. So what you see here is a small operation, a quantum operation, performing the Hadamard operation and to see its measurements of it. And what I first do is I define a number of results and I get a register of qubits. So this is picking my qubit. I then use the Hadamard gate to put a 0 into a superposition, and I use the M gate, the measurement of it, to measure it out again. So what you would expect of this is that this will be 50-50. Now, I have this quantum operation, which is nice, but I now want to use it from C#. So what I have here is a piece of code where I see my Hadamard function and I can interact from C# in there. So what I do is I have my quantum function, I give it a factory, which essentially enables the program to execute this code. In this case, it's a quantum simulator. I'm running, in this case, the Microsoft Quantum Simulator to run this. And as you might see, if it all goes well, you get the output of 1, 0, 0, 0, 0, 0, 1, etc., etc. And if you would add this a lot of times, you would see that it will be 50-50. Well, this is nice. Okay, this is a simulator. And Microsoft has a big simulator for 40 qubits, and you can do a lot of stuff with it. But you want to run on real hardware. So if I change the factory, I can put something else in there. Another execution device. In this case, I'm putting in the IBM QX2. So the IBM QX2 is a real physical quantum computer in the basement of IBM. If I run this converter, it first generates QuASM, which is quantum assembler for this kind of machine. So I will now move to the quantum machines. So these are the IBM quantum computers in their library, within their basement, and I have multiple devices on them. And as you will see, I hope my demo works today. It now schedules. You see the graphical representation of this same code. You see that same Hadamard gate, and you see it being queued on the quantum machine. So once this will start executing, you will see something like this. This is that same code executed on the real physical device. And you see that on the bottom there are all the measurements he can take, and he found that it's currently a 1. Well, this is nice. Let's repeat it a number of times. And you would see that on a real physical device, you would have like almost 50-50 collaboration there. It's a physical device, so it's not perfect yet. Let's see if it's executed. Yeah. So in this case, it tried to queue it on the IBM, wasn't quick enough. So we went to the simulator, and this time it got a 0. Okay. So can we do other stuff with this? So I mean, this is just a simple Hadamard. We have to do the QuArC code. We don't even need to change it. We can run it the same thing on both the simulator and the physical device. So suppose I'm going to do some more complex stuff. Well, I told you about the CNOT gate. So here is that same thing we discussed here, which is the CNOT gate. So I have the Hadamard, which I put it in a superposition, and now I have that same CNOT gate to entangle those bytes, and now I'm going to read it. Now, what you're starting to see here is the interface layer between the quantum computer and the normal traditional computer. I have quantum operations on top, which are executed on the quantum machine, and I have traditional computing to interact with the quantum machine and talk back again. So this is this interaction that I'm currently able to describe. So what we're currently doing here is we put the control bit in a superposition. We're going to perform a CNOT gate, and we're going to check if it's indeed the 0, 0 and the 1, 1 we expect. What you will see is that 49 of the times I get a 0, 51 of the times I get a 1, and they're still in alignment. So this is indeed the case also in the simulator. So then we get into the hello world of quantum computing, the teleport gate. Well, I'm not going to explain this one. It's more of the same, more of the stuff. It's the traditional stuff. But you can describe essentially all the quantum algorithms you will have in here. Things from the textbooks. Well, does it work? Yes, it works. Nice. So how am I going to execute my own programs on this? I mean, my functional requirements don't have these Hadamard gates and these quantum gates in there. Okay, so let's start with something simple. Let's add two numbers together. So, as all programs are, please give me 3 beers. For those who don't get the joke, it's binary. So, in this case, we're going to add 2 numbers together. And what I will be using is the same CNOT gate, because I need, for an adder and a half adder, I need both a sum and a carry. Yeah? The sum is an XOR. We already saw the CNOT gate for that. Now we need the AND gate as well. We're going to use a TOLIFO gate for this. It's a CC0. It's an expanded CNOT. The thing is that you will see that this operation already uses 3 qubits. And there will be one which I currently set to 0, and which will be disposed as waste afterwards. Okay. Will be important later. I execute this, and it's very simple. If anybody is very surprised that 1 plus 1 is 2, 1, 0 in binary, please contact me. So this is simple. We can also do this in normal computing. So now we're going to do the reverse. How much plus how much is 1? How much plus how much is 2? How would you write that in C#? You would normally have a loop, and you would start checking things like results, if you couldn't do the mathematics. Well, the thing is, I told you that quantum or qubits are waves. And waves don't care in which direction they flow. So, if they flow from left to right, it's the same wave as going from right to left. So in this case, because our operation is going from left to right, is an adder operation, we just need to reverse our code, and I have the code from right to left. So what I'm now going to do is I'm going to reverse the adder. So I reverse the operations in order which I executed. And now I need to do something with that waste. I originally had waste, and that waste could be a 0 or a 1. Well, in a quantum computer, a qubit can be both at the same time. So I fill it with something which is in both states at the same time. So what will happen under the hood is I would have my waste being either 0 or 1, and both scenarios will be there in virtual. I get the computation of the adder in reverse, And when I observe it, only one of these possibilities will be returned. So what you will see is the top is expected. I get back 1 and 1, 1 and 0 together make 1. I get back that 1 and 0 are also 1. And then I get the bottom part, which is a bit strange, because according to them 1 and 1 is 2, yeah, that makes sense. But I also get back 0 and 0 is 2. And now you mark the third column, because that's the waste bit I originally filled with 0. So I can recognize my correct results now based on that last bit. That's what we call the oracle. We place a condition on them to filter out the correct results. So we gave a puzzle to the quantum computer. It solved the puzzle by doing all the steps at the same time. But we now need to filter out, like, okay, what's the correct answer in this? And in this case, I use that qubit for it. Now, normally people would think like, yeah, but this is just a normal loop, normal if statement, and just retry, and how many? Well, it's a bit more complex than that. Because what you do is you have something that splits out, 2 to the power of n, and you get back a random state. So you need to first seem to find that one that you're interested in, and you make use of your oracle there. So what you do is you define an oracle function, and that oracle function essentially amplifies the chance that you will be getting back that specific result that you're after, because these are waves. You're not doing normal wave mechanics, you're doing wave amplifications here. Well, algorithms like Grover, Chamal, and things like that do this for you. You don't need to redesign this yourselves. And because it's a redesign, hey, QuArC already gives you functions for this. And you can just model your application and put it in there. Okay, but still, applications which run on the physical machine, yeah, a physical machine is a bit different than the virtual machine, the logical build machine. So you also need to take into consideration, yeah, okay, we have a number of deviations in here. Well, also in that part, Microsoft QuArC offers you error correcting codes, which you can enable in registers and such to get rid of that noise level and essentially create a logical qubit machine for that. And then you're in the operating mode. Okay, so let's get back to my original stuffed animal problem. So I now need to, I know what to do now, right? I need to formulate it as an entanglement problem, like having a wave function for it, and I need to have an oracle function. Well, formulating it as a wave function is a bit of an exercise for this room. This paper is 35 pages, it's heavy mathematical, and it makes use of some more additional heavy advanced details in there. But conceptually it's quite simple. What you will be doing is each qubit would essentially be going up a stairs, and you will be going up all stairs at the same time. And you expand and expand that state space in there. You now need to shrink it down again for the oracle function. And how we do that is we define that oracle function as, if I have no stairs, that will be 0. If I had 1 stairs, it will be Hadamard. And if I would pay 2 stairs, it will be at the bottom. And I would optimize using that same amplification algorithm on that oracle function. Well, very many hours later, reading a lot of papers, you see that bringing this would get you to the square root of the nth factorial. So this n in this case is the amount of places you want to be. And as you can see, the naive approach, it's no contest. Once you get to the bottom, it's kind of a mixed match in certain numbers and you get a trade-over point. So for TSP, we need quite large quantum computers to even do this. So I did this for my home, and I found out, as you might expect, that this is the optimal search solution in finding the cuddly toy. So I told my wife, like, yeah, I now have the optimal search configuration after a lot of computation of searching for Wuffy. And my wife said, I think I have a better solution. Which I might agree upon. So this is quantum computing in a nutshell. It's something which is not simple, and it's way different than how we normally would perform computation. Normally we would have adders and modulos, and a lot of people really like to do that stuff. But this is very, very powerful. You can do a lot of stuff with this. And you can do, when for example, Google will really ship their 72 qubit machines, that will be more than the data centers can provide. So this will be a game changer. We can do things that we didn't even imagine. This will therefore also change the world, because now we can do computation and find out stuff which we couldn't do before. I didn't really show it, but this is also very unstable. We're currently talking research and development stage. This is like a small van in a bunker at IBM in a research and development laboratory, and you get some access keys and some access tokens and you can play on it, but it's not something you can put in production yet. It's not production ready yet. So we're currently at the ENIAC stage, the big physical machines with the valves in there, and things are still, yeah, you need to be replaced and such. It's cool to play on. I mean, it's still accessible if you want to play on, and it works with the traditional Visual Studio tooling and all the normal tooling which is in the corporation, because Microsoft QuArC is based upon the C# frameworks. And it works on real hardware, which is the most fun part to play with. So be part of this quantum revolution and please play along. Are there any questions? Yes, please. Just shout.
Yeah.
I'll repeat it.
Two questions.
Mm-hmm.
First, it used to be F# liquid.
Mm-hmm.
Now it's Q#. Originally it was extension of F#. Now it's Q#.
Yes.
Since it's considered to be like an esoteric language, and even F# considered by some developers, it's something that you need some learning curve. Doesn't it limit the or maybe scare some developers that you have to start learning different language to work with that? So what were the reasons for F# not being sort of compatible with these ideas? And second question, since this is something is sort of not precise, like you're getting observations, the field of application for quantum computing, you can't really have tasks that based on like pure Boolean logic. It's more applicable to something like searching optimal path, like where you accept sort of imprecise answers. Is it correct assumption?
Let's start with the first question. The first question is, they already had an F# extension, which they based upon, which they created Liquid on. Why did they create a new language, and why do they have these interactions? Is that your question essentially? Yeah. Why did they create it? Yes. What you see, and this is second-hand because it was a bit of a discussion, but the impression I'm getting is that in the research and development world, functional programming is quite common. things like Haskell, things like F#, that they're more for those kinds of people. They're easy to work with by those people. But it's not a language that's commonly adopted within normal web development, normal application development. And what they could have done is said like, hey, let's put like a C# extension and then have a quantum version of that and essentially extend the C# language. That would have had some problems, some details in there, which, because you're currently working with statistical models, statistical interactions, you would have a lot of things with nasty for loops and combinations with links. So I can imagine that they took a middle approach there. That they define a new language, Q#, which is still imperative, so it would still have detailed execution where you're not talking in the functional language, but still have the functional components in there. And yeah, if it's all new and a mix of match of both things, yeah, let's just rebrand it as a new language. So I don't know for certain because I don't work for that team, but I think personally it's somewhere in that space. Then the second question. The second question is, since quantum computers are statistically driven, are based upon things which aren't Boolean-wise, not true and false, are they not more optimized for optimization problems? Are they not more accustomed to good enough algorithms? The answer is yes, that's where the most powerful computation lies, where it's a good enough approach, and there's where the best algorithms already exist. What you currently are able to see, this is the IBM machine, which is a gate-based machine. There was already a quantum computer from D-Wave, which was an annihilator. They're currently at 1,024 qubits. 2048 is already around the horizon. But that was a generation 1 machine. And it can only deliver certain approximations and such. So our first generation were approximations, and now we're starting to get into real gate processing machines which can handle those delicate 1-true machines. So yes, the easiest case for quantum computers are more like the good enough approximations, but we're currently starting to move into that a quantum computer can also be used for this more detailed Boolean operations. Does that answer your question a bit, or?
Yeah, just to clarify, can you? There are a lot of traditional calculator demos. Can you build with Q# demo of calculator that would give you precise answers to like 2 power 2 or 1 plus 1?
Depends a bit. If you would be a university person, your answer would be no. If you would be a business person, your answer would be yes. The answer will be no because your answer is not guaranteed. So there is a very, and add like 2 to the power 32 varies in there, low possibility that you will never get an answer to a computation. In reality, usually the chance of that happening is so low you don't care. You just rerun the execution, just perform it out. That's where the things like, I use the until, I use the amplification in there to really enforce like, I want to have this answer and please give me this answer. And I make the probability of getting that answer higher and higher and higher and higher. And the more certain I want to be of that answer, the more iterations I will put in there. So for a university student, no. For a business person, even precise will be good enough. Any other questions?
Thank you for the talk. And while you do demo Q# gates, is it like the machine, does it limit the kind of configurations you can apply into? So can you apply like all H gates for all the qubits, or does it partition qubits somehow? Those qubits are for H gates, those qubits are for NOT gates. So how it is at execution level?
If I understand your question correctly, the QSharp language, does it limit you in what you can model?
Not the QSharp, but the machine itself.
The machine itself?
Yeah.
Yeah, that's a good point. So this is, I go back to the physical machine again. And we're currently at this tech level, right? I mean, most people of you have played SimCity, you're at a certain tech level in your tech tree. What you see here on the left is the IBM QX5, which is a 16-qubit machine. And what you see beneath the chip and a diagram is a small graph. And what this graph is are the trenches which is in the physical silicon of qubits which are able to talk to each other. So in case of the IBM Q machine, there are restrictions in amount of qubits I can use, and there are limitations in which qubits can talk to each other and which qubits I can entangle with each other. So yes, in the physical device, there are currently limitations. However, what you're seeing is, and this is a more advanced device, this is the QS11, which is a 20-qubit machine. If you're part of the partner program, you can get access time to this one. And here the slots are two-way. And you can see in kind of a matching pattern here, where you're seeing that the physical qubits are getting arranged in a pattern to be able to do all kinds of computations in here. And what you will probably see, and which I'm expecting, is that there will be a logical layer on top of this, which is less restricted. They will have a limited number of qubits, but you would have logical qubits on top of this, on this physical layer. Does that answer your question? Okay, thank you.
Any other questions?
How it works in multitasking environment? Is it possible to support multitasking? Or
this is a multitasking environment. Essentially, we use this is like what engineers call the physics package. So it's a dedicated thing, it executes, and you hope that nothing, it's single use. There is a big queue in front of this. So what I did, and that's why I didn't execute directly, I think you can still see it here. No, that's this one. Is that my job is scheduled. We're currently at the 50s mainframe era, where you can put in jobs, and these jobs are scheduled, and you get the results back. And that's currently how multi-tenance is done on a quantum computer.
Does the state of machine is saved? I don't really understand how does switching between tasks works. That the state of the qubit is saved, or how it works in
No.
No?
That's the problem.
Okay.
That's the problem. The thing is, why is this difficult? We create this superposition, this entanglement, and I said, like, if you do a measurement, it falls apart and I get a 1 or a 0, get the computation. Measurement does not mean that I do it. Measurement means also that a ray from space, a gamma ray or a photon hits it, that's a measurement. So it falls apart. So we already have, and we're limited currently to, I thought it was 100 milliseconds of space currently. In the times we can keep this superposition in there. So how it technically, and I'm making some summaries here now, is you have this chip in there, and you have the radio waves coming in, and it creates a resonance bubble bath. And this will be in flux, it will be a resonance frequency, and my program will then be converted to noise, like a noise pattern, a radio pattern, and this radio pattern will be injected into this bubble bath. It will do its magic, and then the noise pattern, the interference pattern which comes from that noise path will be sucked out again, and that will be measured. And then the complete machine is flushed out, a new resonance will be created, and the next operation takes place. So there is no storage, you only have the measurements coming out and the noise you put in. That's it. But that's how you've performed the calculations. That also means that your data needs to be part of your program there.
Yeah, can you please expand on timing? I mean, you did show that, 100 milliseconds is the time frame we can keep this interference, right? And how long does it take to prepare for the experiment? I mean, does it take hours to prepare the machine for the computation? Does it take minutes, or what are the time frames for the computation in like end-to-end case?
Oh, this is a real physical execution of such a machine, like an execution here. And what you see here is the calibration statistics. And what you see here is that currently I'm operating, because it's a very small gate, at 14 microseconds in there. So this is a job which took a few, like a second or something. Normally within half a second they have this processed. It gets put into the machine, I get a result back already. It's just that the amount of gates I can place in there, like the complexity of the noise channel, that's limited. Does that answer your question? Okay, thank you. Please.
When you said that it's not stable and because of that not production ready, so what is not stable? Because if I see that it gives me computational advantages, that I can really get results quicker, then why can't I rely on it? Is it great risk of getting a wrong result?
It's very it's research and development still. And yes, it has capabilities, yes, it has business impact, yes, it has a return of investment there, but you're still talking about something which basically grew out of a university. You're putting into production something a student built. These are professors, but same idea. So this isn't built for scale yet. This isn't built for resilience yet. We don't have like 2 quantum computers to have resilience if one fails, like those kinds of things. We're not talking that kind of operational level yet. But still, even though that's not, for some things that's not even a problem. If you have things like computation where you need this kind of stuff, if the building burns down, who cares, right? So it depends. But do know that this is still highly experimental. Even during debugging this morning, my demos, I already hit another defect which I need to file again. It's still very in development, it's very new stuff. Half of the MSDN of this is references to papers and formulas and such. We're not at the end game there. But it's if you need the capabilities, if you need the power, if you need this kind of computational power, it's already available. And it will only get faster and faster and faster.
So, friends, that's all. And Rolf will be in the third discussion zone. You can ask him for questions, some more questions. And thank you very much.
Thank you.